As climate change intensifies, there has been an increased focus on curbing CO2 emissions. Hydrogen has emerged as a promising energy source for solving these issues. However, there are numerous challenges related to production, distribution, and the end use of hydrogen, namely establishing a link between hydrogen purity requirements, as impurities like hydrocarbons and inert gases can harm the fuel cell. The majority of hydrogen produced worldwide is accomplished by steam methane reforming. In this process, methane from natural gas is reacted with steam to produce synthesis gas, a mixture consisting principally of hydrogen and carbon monoxide. There are reported values for the recovered hydrogen gas from steam methane reforming. We estimated the composition of the stream before it underwent steam methane reforming, i.e. the raw feedstock. We'll go on to explain the math.
So yeah, we went ahead and used the conditions given in the problem or in the article, which is 306.45 Kelvin and 26.3 bar. I went ahead and found the molar volumes for everything in the NIST tables and went ahead and set up our vapor fraction chart, our vapor phase chart. H2O is in liquid phase, so that has its own little section. And we put all of those in terms of the extent of reaction. We then found delta G at 298 by calculating all the delta G's of formation and finding the reaction. And we used that to find our equilibrium constant at 298, which we ended up being able to correct for temperature values. But since 306 is really close to 298 Kelvin, we assume that delta H is independent of temperature. And so we were able to solve for K being 1.01 times 10 to the 30 power. We then found our Z values,
The compressibility
factors, which we were able to use in our Redlich-Kwong EOS so that we could find the viscosity coefficients for all of our gas phases, and we ended up finding those, as well as our overall B, which helped us in the end find these values right here. And so using that, we also were able to find the activity coefficient of the H2O, which ended up just being 1. And we plugged that all into this equation right here using the K that we found earlier, and we plugged it into a solver, making sure all of our terms were in the extent of reaction, and we found that the extent of reaction was 0.98, and all of our vapor fractions are right here.